All right, gentlemen, let's move on. We already, prove this, and I hope the proof is clear. So now let's talk another important thing, important concept that we are going to use a lot. This beautiful little guy here, we call this unit vector. As you know from its name, right, unit vector means a vector whose length is 1. We call this a unit vector. So simply, to actually get a unit vector, for example, in two-dimensional space, let's say, right, if you just draw a unit circle. If you just draw a unit circle here, that is x sub 1, and this one is x sub 2, let's say, and that is our unit circle. This one is 1, and that is -1, and here we have -1, and this is 1. That means that any vector whose head is on this circle, right, that is a unit vector. All unit vectors are here. For example, let's say one unit vector is this, right? It may have some different coordinates. Another one is this, another unit vector. For example, this one is another unit vector, and this one is another unit vector. Among these unit vectors, actually, two are really important. The unit vectors which are on the x-axis and y-axis. Let me just know this with green line. This unit vector and this unit vector. They are really important comparing to others. Why? Because they are really easy to deal with these vectors. Because their components, what is the components of this vector? It is just 1, 0. And how about this one? It is just 0, 1. But if you take other vectors, for example, let's say this one, what are the components? Maybe it is 1 over square root of 2, and let me just write like this. Okay, maybe it is 1 over square root of 2 and 1 over square root of 2. As you see, just 1, 0, 0, 1, 1 over square root of 2, right? It is easy to deal with these numbers. And also, actually, if some of you are from computer science faculty, right, or department, you are studying computer science, that's why they chose the 0, 1s, just two numbers, 1 and 0. Using these numbers, right, the combination, we can form a lot of things, right? Just we have 1, 0, I can write 4 different things. How about if you have 5? How about if you have 6? How about 8? Anyway, so these vectors, actually, we will just name them as standard unit vectors. So these are usually, we denote this with I, J, or just simply, I can also denote this with I, E sub 1, whose coordinates are 1, 0. And this one is, what is it? E sub 2, whose coordinates are 0, 1. And how about in three-dimensional space? That is, let's say, here we have I, J, K. Anyway, in three-dimensional space, our standard unit vectors are 1, 0, 0. And second one is E sub 2, that is 0, 1, 0. And E sub 3, that is 0, 0, 1. Right. And in three-dimensional space, if you just draw a kind of sphere, right? The sphere, here we have sphere, let's say, and here we have sphere. Okay. And all the vectors, position vectors, whose head is on the surface of this sphere, they are unit vectors. And once again, among them, these vectors are, or let's say, play a really important role in describing a lot of things. They're really easy. And that's why actually they deserve to have a special name. Their name is, what is it? Standard unit vectors. So in general, if we generalize this in R2, in two-dimensional space, this 1, 0 and 0, 1, these are the unit vectors. In R3, that is 1, 0, 0, 0, 1, 0, and 0, 0, 1. These are the standard unit vectors. In general, if you just generalize this to n-dimensional space, what will be the, what is it, standard unit vectors? These are E sub 1, E sub 2, and E sub m. Actually, I'm going to use this a lot in the future. That's why you need to know them very well. So where EI has 1 in its ith component and zeros elsewhere. So these vectors arise repeatedly in linear algebra, and they are called the standard unit vectors. Okay, that means that this E sub I, what we mean by this? That is, here we have 0, 0, blah, blah. Here we have 1, 0. So that one is I's component. Right? Let's see here, this E sub 1 means the first component is 1, the rest is 0. E sub 2 means the second component is 1 and the rest is 0. And here, E sub 3, the third component is 1 and the rest of the components are 0 on the top. All right. Normalize a vector. Another thing that you should know this, sometimes you're going to use this thing. How do you normalize the vector? Normalize means how actually change this into a unit vector. To do this one, we know that if you just divide any vector, right, by its norm, it becomes a unit vector. That is how we normalize a vector. Okay, why? Because the length here we have, let's say here we have V, we don't know the length is, right? If I just divide this, for example, let's say the length of this vector is 5, right? If I just divide this into 5 pieces, then it becomes unit vector. So we'll have 5 unit vectors. Let's say here we have 1, 2, 3, 4, and 5. Okay, so that is our unit vector. Okay, in the same direction, but only the length is 1. Okay, so to normalize this vector, first we need to find its norm. So the norm of this vector, that is the length, that's equal to -1 squared plus 2 squared plus 2 times square root of 11 squared, which is equal to square root of 1 plus 1 plus 4 plus 4 times 11, that is 44, which is equal to 48, and 49, that's equal to 7. The first step. And how about the second step? So we have to divide, right, by, this vector by its length. That means that we need to divide each component. Dividing means multiplication, right? So the unit vector in the direction of V, that's the unit vector in the direction of V, will be V over the length of V, which is equal to, what is this? It is something like this, 1 over norm of V times, and here we have vector V, and which is equal to, we know the length of this, that's equal to 1 over 7. And how about vector V? It is -1, 2, 2 times square root of 11. So we know how to multiply, right, a vector by a scalar. As you know, just we need to multiply each component by 1 over 7. So here we have -1 over 7, 2 over 7, 2 times square root of 11 over 7. Okay, so we have just normalized this vector. Okay, that is all about normalizing a vector. And here we are going to see 2 important inequalities. Okay, the first one is Cauchy-Schwarz inequality. For all vectors u and v in Rn, the absolute value of u dot v is less than or equal to, what is it? The product of the norm of u and the norm of v, right? So you may wonder why we are putting absolute value. If you do not put absolute value, right? For example, let's say if you just have like this, u times u dot v, and we know that when it is negative, on the right-hand side, we have positive. And positive always greater than negative, and nothing to prove here, right? So the thing is, how about the absolute value if it is positive then? If you just take the absolute value of u dot v, Is it still less than or equal to this or not? All right, that is our interest here. Okay, because if there's no absolute value with minus sign, there's nothing to do. So this thing is not so easy. For general form, we are going to prove this maybe in chapter 7 later. Okay, but here, what I want you to do is you need to try, for example, for let's say for two-dimensional space, okay, three-dimensional space. Okay, you need to try this if you are interested. That means that assume that this u and v, because this one is Rn, what is n? We know that from here n is greater than or equal to 1. Right, actually here we have dot product. When we just say dot product, it is 1 means here we have only one component, so that's equal, here we will have equal. When it is two-dimensional space, actually it works for any dimension. That's why, particularly, how about if u and v are from two-dimensional space? Does it work? Try this one, and after that, try the second one. All right, u and v is from three-dimensional space. For example, if you consider the first case, for example, let's say u and v are from two-dimensional space. What we have here? Here, that means that u, it has two components, right? Here we have u1 and u2. And v, and also it has two components, v1 and v2. And this inequality, I will just write something equivalent to this inequality. What is it? The left-hand side, it is positive. Right-hand side, it is positive. Since these things are positive, so that is the same thing as this thing. That is u dot v, since both sides are positive. If I square, the inequality does not get affected. Here we have squared times v squared. Okay? And since u dot v, here we have, when we have squared, now we don't have to write this absolute value, right? The symbol. So I can just write, I'm going to prove this thing, u dot v squared is less than or equal to norm of u squared, norm of v squared. If we can prove this thing, that means that we will have proved also this inequality. Why? Because these two things are equivalent. To do this, we know what it means, right? U dot v for two-dimensional space, that is, what is it? U sub 1 times v sub 1 plus u sub 2 times v sub 2, right? The sum of the product of their corresponding components. And here we have square. Here we have square. I'm hoping that that is less than or equal to, how about this thing? That means that here we have u1, right, squared plus u2 squared. And here we have v1 squared plus v2 squared. Okay. So how do you prove this now? What is it? We just simply have algebraic inequality here. We do not have any vectors here, right? We have only real numbers here. So can I just hit, let me just denote this with, let's say this left-hand side, and this one is right-hand side. Okay, and I'm claiming that right-hand side is greater than or equal to left-hand side. That means that that is the same thing as this. Can we just prove this thing? Right-hand side minus left-hand side is greater than or equal to 0. Can we prove this? If we can prove that, that means that the same thing, we will have proved this inequality. To do this one, if you just remove the brackets, guys, I will just stop after writing this one. Okay, we are just going deeper. You can, this is an exercise for you, and also you will see that from your book. I think it is an exercise 71 and 72. So this is the idea. So now if you just write the right-hand side, what we have here, I need to multiply this by this, this by this, and this by this, right? So here we will have u1 squared, v1 squared, plus u1 squared, v2 squared. And the second one is here u2 squared v1 squared plus u2 squared v2 squared minus, and how about left hand side? Left hand side equals this. If you remove the brackets, here we have u1 squared, right? v1 squared minus 2 times u1 v1, 2 times u1 v1, u2 v2, u2 v2 minus, here we have u2 squared v2 squared. And now equals, I don't know, actually it's less greater than or equal to 0. Here we have u1 v1, right? Do we have u1 v1 here? Yes, here we have u1 v1 squared, u1 v1 squared. So these things are gone. And similarly, here we have u2 v2, right? Squared minus u2 v2 squared. Also, these things are gone, right? So what is left here? Here we have this thing. Let me just rewrite here. u1 squared v2 squared minus, first let me just write this term here, u2 times u1 v2. Let me just write like this, times u1 v2 times here we have, what is it? Here we have, second one is u2 v1. So here we have u2 v1, u2 v1. And plus, what we have here? Here we have u2 squared v1 squared. If you notice here, what we have here is something like this, right? Here we have a squared minus 2ab plus b squared, which is equal to a minus b squared. It's a perfect square. So, are we recording? Good, it's recording. So here is exactly the same thing here. If you just take this u1 v2 as a, u2 v1 as b, here the product of these two things, I can just write here as u1 v1 minus, sorry, v2 minus, here we have u2 v1 squared. Now we know we have a real number and the square here. We know that the square of any real number is always non-zero. And this proves that, actually, this proves that that's true, right? That means that this is true. That means that this is true, because if you just take this to the right-hand side, that means that this is true. That means that this is true. So from here, we say you can write that absolute value of u dot v is always less than or equal to the product of the norm of u and the norm of v. That is the proof of this for two-dimensional space. In similar way, what you have to do is for this. How about if you just take two vectors from three-dimensional space? Is it true or not? There are some different proofs. You can search on internet and Google. Okay, you can have a look to get some idea. Anyway, that is the Cauchy-Schwarz inequality. You know, in the test, I may ask you, for example, choose a Cauchy-Schwarz inequality from the below. Okay, I'll give you 5, for example, and if you choose, you may have this kind of question. Or proving, I may give you as a project. You have to present it. We will see. Anyway, for now, that much is enough about Cauchy-Schwarz inequality. Now we have another inequality, important inequality. It is the triangle inequality. Why actually we call this triangle inequality? Because from the property of triangle. Because we know that if you are given any triangle, right? Let's say we are given any triangle. Okay. Let's say this side is A, this side is B. Okay, so it looks a bit weird. Let me draw again. Let me draw something like this. Okay, sometimes tablet is not easy to draw. All right, now it looks much better. Let's say this side is A, this side is B, and this side is C, right? To be able to construct a triangle with this A, B, C, we have 3 line segments. Let's say this line segment A, it is B and C. And from here, we know that the sum of 2 sides, here, let's say this A plus B always must be greater than C, right? Otherwise, we cannot construct a triangle. If the sum of this equals C, it will be just a straight line. So the sum of this A plus B must be greater than the length of the third side, right? That is true for all other sides, like A plus C, it must be greater than B, or B plus C, it must be greater than A. Actually, you studied this in grade 6 or 7, if you can remember. All right. How about here? From here, triangle, again, I can just write, let's say we are given 2 triangles, and because if you're given 3 vectors, we can form triangle, right? And that is, let's say, vector V. And how about this? And by vector addition, right? U plus V, that's a displacement. And what is the length of this vector? That is just U plus V, right? So here, if I just take this, here we are saying that this the length of U plus V is greater than the sum of U and V. Okay, so we are forming a triangle. That's why it is called triangle inequality. Okay. Why is it so? Proof is not so difficult. Again, as you see here, left-hand side is just a length. That means it is positive. That means that's non-negative. Right-hand side is the sum of 2 norms. Norm is always non-negative. That is non-negative, non-negative, right? So if I can prove that, this U plus V squared is less than or equal to norm of U plus norm of V squared, then that means I will have proved this inequality. Okay, good, because it is positive. If you just square both sides, it does not affect the solution of this inequality. That means that it will produce equivalent inequality. So using this fact, let's use purple here. How do you prove this? Here we have, starting from left-hand side. So here we have the norm of U plus V squared. And by the definition, what does it mean? This means that's, right, square, right? That is just U plus V dot U plus V, right? And we have just already proved this in the example, if you remember. That is equal to, actually, I don't need this. Let me just delete this. Okay, just distraction. And if you remember, how did we expand this? That's just equal to, here we have U dot U plus, right, 2 times U dot V. These are vectors, don't forget. And here we have V times V. That is V dot V. It's very similar to perfect square. Now, we know that U dot U, right? If I just here, it's positive. It is positive. I have nothing to do, right? And also we know that that just gives us the square of this norm. And also it gives us the square of this norm. But how about this U dot V? I don't know, it is negative or it's positive. But if I just put here absolute value, then this thing will be less than, or equal to, this is just the norm of U, that is the norm of U squared, plus here we have 2 times U dot V, right? I just put absolute value because we know that if you just pick any number, any real number, that number is always less than or equal to absolute value of A. I'm just using this fact because if A is positive, A is equal to itself. If A is negative, right, this is positive, so negative number, it is less than this number. We have 2 possibilities. This is how we describe this symbolically. So I just change this brackets into absolute value, so this will be less than or equal to this thing. Plus, how about V dot V? By the definition, that's just equal to V squared. Excuse me. So, and also using the previous inequality, right? Now, as see here, we have absolute value U dot V. Now I'm going to use the Cauchy-Schwarz inequality for this. As see here, absolute value u dot v is less than or equal to the product of these two things, right? So if I change this now, we will have here less than or equal to. Again, here we have the norm of u squared plus here we have 2 times the norm of u, right, times the norm of v, and plus the norm of v squared. Now what we have here, as you see here, a squared plus 2 times a times b plus b squared is just a perfect square. It's a number, positive number, it's a number. So that's just simply equal to norm of u plus norm of v squared, right? So here, because of this inequality sign, that means that this thing is less than or equal to this thing. This implies that then u plus v, I mean their norm, is less than or equal to, if you just remove the squares, right, this squares, that is less than or equal to norm of u plus norm of v. That is a proof of triangle inequality. Okay, guys, any question?
No, sir.
Sorry, say again.
No questions, sir.
Is everything clear? Do you understand? If you are there,
Yes, sir.
good. I mean, if everything is clear, you understand everything is good. These are very basic concepts. Good. Let's continue. Now, guys, we need to define another important concept: distance. Distance between two vectors. All right. How do we define the distance between two vectors? The distance between two vectors is just the direct analog of the distance between 2 points on the real number line, or 2 points in the Cartesian plane, right? If you just form one-dimensional space, for example, let's say here we are given only number line, we have everything is here. If you are given two numbers, let's say this one is b, and here we have a, right? And how do you find the distance between these two numbers? As you know, if I just write here d, if I know that a is greater than b, actually the distance is just a minus b. But if I don't know which one is greater, to make sure that it's positive, because distance must be positive. So just to make sure that if I don't know which one is greater here, then we just put absolute value to make sure that the answer will be positive. So this is how we define this, right? And also, two-dimensional space, if you're given 2 points, for example, let's say this is point 1, point 2, let's say this one is point A and point B, and coordinates are, let's say this one is x1, y1, this one is x1, x2, y2, right? This one is x1, y1, and this one is x2, y2. How do you define this? From coordinate geometry, the distance between these 2 points, right? Actually, to make actually here there's the distance, but we just put this vertical lines here. So that is square root of, what is it? x1 minus x2 squared plus y1 minus y2 squared. Okay. And similar to this. Okay, guys, we have 10 minutes. Good, I'll finish it soon. How about if you're given two vectors? And let's say this one is vector u, and another one is, let's say this one is vector v, right? The question, the distance means, what actually mean by the distance? We mean the distance is the distance between their heads, this one, okay? That is the distance between u and v. This is how we define the distance, okay? And as see here, the coordinates are, this one is, let's say, v1, v2. Just an example, because here it's from n-dimensional space, right? It means that they have n components, but it's very similar to this. So here we have u1, u2. It's like just finding the distance between 2 points. And that's why it's just equal to u minus v norm. And from this norm, you know what we mean, right? If I just write here for this, what is the norm of u minus v? That is equal to, we know that it's just u minus v dots, u minus v, or that's just equal to what we have here. Here we have norm, right? And here we have u minus v means u1 minus v1, and here we have u2 minus v2. And norm of this vector, which is equal to square root of u1 minus v1 squared. That is the square of the difference of the x coordinates plus and u2 minus v2, the difference of the second coordinates, y coordinates. And here we have squared. Right? It's exactly the same. So this is how we define. As I say here, in very compact form, this is how we define the distance between two vectors. When we say distance, we mean, as I here, the distance between their heads. Immediately, let's see one example for this. Find the distance between the vectors v and u. So the distance between u and v, that is equal to just the norm of u minus v, which is equal to square root of -1 minus 3 squared plus 2 minus 4 squared, right? 2 minus 4 squared plus, and here we have -11 minus 0 squared. All right, let's close this. Equals -1 minus 3, -4 square is 16 plus 2 minus 4 is -2 squared. That's equal to 4 plus square root of 11 minus 0. Square root of 11 is square is 11. So here we have 11, which is equal to square root of 31. That is the exact distance between these two vectors. All right, angles. How many slides we have? 1, 2, 3, 4, 5. Okay. Okay, angles. Guys, let me stop here. I think it's too long and you must be tired. Thank you very much if you are there for listening. If you are not there, you have to study these concepts and watch. As you know, last time I shared a link, okay, and all materials related to this course, I will try to put them there, and updates maybe weekly or every Wednesday or Friday once I teach, right after I teach, okay. If there's any new material, I will put them there in different folders. So you can reach these lesson videos or let's say notes or the book and blah, blah, blah through this link. All right. So guys, we will meet on Friday on purpose. Actually, I want to leave one day. Okay. You need to sit and do your assignments today. I will send you your assignment number 1. As I told you, I will divide it into 2 groups. One group, they have to solve odd numbered questions from each exercise. Second group, even numbered questions. How you have to do this, you need to solve them on A4 size paper. At the top, write the exercise name and your name and course name. Draw a line with the ruler, then solve it. It must be on every page, okay? Like leave 2 centimeters at the top. And also from the bottom, always leave like at least 1 centimeter, because when you scan, it looks better. Otherwise, sometimes it's really messy. And also I will actually evaluate your handwriting. If it is too messy, you may not be able to get full score. Okay, thank you very much. See you on Friday. Bye-bye.
Right, sir.
Bye. Okay, Adam said yes. All right, good.